It's great to see so many people here. Of course, we have a superstar coming visiting us, so it's nice to hear. We're looking forward to the talk. I'd just like to do the acknowledgement of country, acknowledge that we're on the lands that are occupied by the Wurundjeri people of the Kulin Nation. And we're here today for a special privilege to hear Professor Chris Manning, who's a professor, the Thomas M. Seymour Professor in Machine Learning at Stanford University. So everybody knows Chris, right? He's the most cited NLP researcher. He's written 2 textbooks. He's done all kinds of really groundbreaking research. His students, Zocher, I believe, right? He took neural networks from vision and he brought them into NLP in 2013, as I recall. That was at least my memory, my experience. And so I think it's really, really nice that we have a chance to hear Chris's reminiscences, Chris's thoughts, Chris's ideas of where things are going, what's the future. Chris, you may know, is an Australian, just as background knowledge, from a place called Bundaberg. Bundaberg. There we go. Chris Manning.
Okay. Well, I guess I'm going to be over here. Well, yeah. Thanks, Ed, for the kind introduction. And so for today, I mean, what I'm going to talk about is in 2 parts. The first part is much more general and historical about where we are with the emergence of large language models and how what we have now as artificial intelligence might or might not be intelligent. And then in the second part, I'm going to talk rather more specifically and technically about some of the work we've been doing more recently in steering large language models with the technique of direct preference optimization. So hopefully everyone will like at least one half of the talk. That's the goal. Hey. Yeah, so, I mean, I thought that, I should give some kind of long-term perspective on the emergence of neural networks and large language models because, nowadays that I'm sort of turning into more of an old person in the field, I'm sort of hit by these feelings of who should you take your large language model wisdom from in 2025? Should you be taking it from someone like me, or should you be taking it from one of these young people like Ilya Sutskever who are hard at work at building large foundation models? And well, the truth is, for lots of the details of building large language models, Ilya knows rather more about and has rather more experience than I do. But I think on some of the longer term issues, hopefully I've got more context and wisdom and experience. So I first went to an NLP conference, ACL, in 1993. It was a very different world for conferences in those days than it is now. Firstly, the technology was very different. This isn't actually a picture from ACL 1993 because I couldn't find any, but it shows the essential technology of the early 90s academic conference where we had these things called overhead projectors. Have people seen overhead projectors? Older members of the audience? Where, you printed things on sheets of plastic and, anyway, I mean, ACL in those days was a very small conference, right? It was held in one lecture hall of a university, a smaller lecture hall than this, I think, and, had 150 people or something show up at it, and ACL 1993 had about 35 papers that were presented over 3 days. Totally different to the scene these days where big NLP or machine learning conferences have thousands and thousands of papers being presented to audiences, sometimes reaching into the 5 digits. But here we were in 1993, and, it was an exciting time in 1993. This was in the early years of when empirical methods and doing what was then often called statistical NLP had sort of just burst on the scene and was a very exciting, and that's what, directed my career at that point. I'd sort of gone from sort of early work on symbolic NLP, which had sort of dominated in the 1980s, and I'd as a young student, I think you benefit from getting into new things. And I'd sort of, digital text has started to become available, and some people were starting to do statistical NLP, and that seemed really exciting. And so I got involved in that. And indeed, at ACL 1993, I presented my first ever paper on statistical NLP. And so the question then is, well, where were language models then? Were there papers about language models? And the answer to that is no. I mean, there were, at ACL 1993, there were 0 papers that were talking about language models. There are actually precisely 2 papers that mentioned language models. So these were the 2 papers that mentioned language models. So Pereira, Tishby, and Lee had a paper about distributional clustering of English words, and they were presenting the perspective that if you could cluster words, you could produce class-based models. And so a possible application of their clustering that they mentioned was language models. And then the other paper was from Fred Jelinek's group at IBM, and we'll come back to them in a moment. But in this paper, towards history-based grammars, they were basically starting from the starting point that we want to be able to do language understanding, and that's not really going to work where we want to actually understand sentences if all we have is a language model. And so we should be starting to put probabilistic models over richer grammar-based structures, and that's what they're exploring in their probabilistic parsing. And so with 2020's viewpoint, I mean, this is really weird. Like, why was no one working on language models? How did they hope to get to artificial intelligence if they weren't even building language models? And, it's not because people didn't know about language models. Language models had existed for a very long time. So how far you want to go back depends on how far you want to count, right? If you want to, you can go right back to 1913. So that was when Andrei Markov invented, well, what statisticians thank him for was inventing Markov models, of inventing sequence-based statistical models. But actually, the very application that motivated, or the exemplary application that he used to motivate Markov models, was actually a language model, slightly generously construed. Actually, he was taking Eugene Onegin, a famous Russian poem, and he was counting how commonly there are transitions from a vowel to a consonant, consonant to consonant, vowel to vowel. So in modern NLP talk, he was building a class-based character n-gram model. But that was a simple language model. And then from there, much of the seminal work on information theory came out around 1950 from Claude Shannon, but as well as general concepts like entropy and mutual information, and lots of things. If you use PyTorch or something these days and you're using cross-entropy loss, right, that's a notion straight from Shannon. But he very explicitly also worked on these n-gram language models, which are sort of tabular language models where you're predicting a next word based on a few preceding words. And Shannon explored small versions of both character and word level language models. Though I think the sort of real credit for language models as a technological tool really goes with Fred Jelinek's IBM group starting around 1975. So among other things, the name language model comes from them, and that they really developed the idea that these probabilistic models, that we could use them for all kinds of NLP engineering applications, using them for speech recognition, for machine translation, context-sensitive spelling correction. All of these were coming out of language models. And so the interesting thing is, from the mid-1970s forward, and more so in the 1980s, and even going forward from there, I mean, language models were a key NLP technology. We all knew that they were very useful, right? If you were going to be building a statistical machine translation system, absolutely, really, the most important part was the language model. But still, we weren't really thinking of those as artificial intelligence, right? They were seen as just this sort of useful statistical thing that you could predict a little bit of local context from. That if you actually um, wanted to get towards artificial intelligence, if you wanted to have these intelligent machines that could reason and plan and understand ideas and express them in natural language, that just didn't seem to have anything to do with language models. That has seemed to have everything to do, at least if you're an NLP person, with the kind of NLP stack that everybody developed in those days, that what we needed to do was build parsers that parse sentences, and then we had to build semantic interpretation systems, and we need to build textual planning systems and generators and all the kind of stuff that people like Ed and me used to work on in those decades. That was the path to artificial intelligence, not large language models. So what was necessary to get to this modern conception of large language models? You know, I was having a lunch with a bunch of 20-year-olds a few weeks ago, and there was the topic of, you know, what was vital for the future of artificial intelligence. And you know, what they had in their heads was it's all about data. It was data that made it possible to have artificial intelligence. And, you know, I think that that's a version of events that people have picked up from the story that's normally told about computer vision. So my sort of stereotyped story of the history of computer vision goes about like this. That for nearly all of the history of computer vision, people did minute experiments on minute amounts of data, trying to do things of finding edge detectors and boundaries and things like that. And then it wasn't until the mid-2000s decade that there started to be small but, you know, modern style labeled machine learning vision data sets. So ones with, you know, a few thousand images and some number of classes, ones like Caltech and CFAR and things like that. And then computer vision was revolutionized, and the problem of object recognition was solved by building this big, huge data set, ImageNet, that then came out around 2010. So I think compared to that, the history in the NLP case was actually sort of interestingly different. So here's the history of large language models in NLP. I did a little bit of searching back in the history. So if you just look for the trigram large language model, the first place it ever seems to appear is in this 1998 paper at an obscure Taipei conference, where the topic there is sort of how do you store and index this large amount of text, 200 million words, but that's not really much to do with our current large language models. So the first thing that really gets us on the track to our current large language models is Yoshua Bengio and colleagues' neural probabilistic language model in 2000. So that pioneered the idea of having distributed neural representations of words, which proved to be such a good idea in the following decades. But, you know, they had the problem that they had almost no computational power. This was before the development of GPUs and just before computers had much memory. You know, when I was a kid, you know, we used to have these computers that, you know, you were lucky if they had 64 meg of memory, right? You just couldn't do much with them. So they had to work with sort of small vocabs and small amounts of data. So they just didn't have enough compute to do a lot. But where the NLP history deviates is look at 2007. In 2007, there was a large language model, indeed it's right in the name of the paper, large language model, which was being trained on a 2 trillion token corpus. This was Google, and so they'd come up with the idea of we can reuse our web crawl to build an enormous language model, which they proceeded to do. So they had no shortage of data whatsoever. But their problem was that they hadn't yet been hip shipped to neural networks. And so they were still building one of these, tabular n-gram-based models where you're using a few words of context to give probabilities for predicting the next word. So their problem was that they didn't have enough modeling flexibility to actually get into business. Then in 2018, we started to see the beginnings of large language models, the original GPT model and the BERT model from Google. And so it was really there when they were starting to build that model that we now started to get large-scale compute. But they were back to not using enough data. That model was only built from 3.3 billion words of data. So, there we're back to not enough data. And so then everything came together in the 2020s when we had models that had all three of these things, which are then essentially our trinity of modern deep learning, that you need the parallel compute, the data, and you need the model flexibility. And then your machines work. Yeah, but, with hindsight, though, the idea that you can make progress on language understanding, language generation, reasoning, and artificial intelligence by just building a language model that's very, very big, I mean, that was a very out and left field idea, right? It's just not the way anyone had been thinking in AI. If people had realized it earlier, even though it took time for computing technology to develop, we could have been doing this much earlier, right? There's no fundamental reason why in the 2000s and the early 2010s we couldn't have been starting to build these systems, even if they weren't as big as the current ones. So it was really the conceptual change of thinking this might actually give us a pathway to learn stuff that was the weird thing. And I think part of what held people back is actually coming to an appreciation of understanding where this seemed possible. Can you just take a lot of text and build a very large word prediction machine and see that as giving you intelligence? Many people sort of feel that sort of just in principle impossible. In fact, there are some people that still feel it's impossible. So in recent times, this argument has most prominently been made by Bender and Kohler. And so Bender and Kohler present, not a weird position. I mean, in some sense, the position they present as the mainstream position of philosophy of language and linguistic semantics. And they say linguistic meaning is the relation between a linguistic form and a communicative intent. A language model, it's just predicting form. Which word follows previous words? So there's no mapping to a communicative intent, and therefore a large language model, in principle, cannot lead to the learning of meaning. Now, I think this is wrong. I think, intuitively most people think it's wrong because you fire up ChatGPT in the browser and you type a sentence to it and it says something back that looks like it's understood your sentence. It certainly feels like it understands things. But Bender and Kohler would argue, no, this is just very clever stochastic parrot text generation where it puts appropriate tokens after the previous tokens. It understood nothing because there's no explicit mapping between linguistic form and communicative intent. The idea that this argument might not actually be persuasive had been argued decades earlier, most famously by the philosopher Ludwig Wittgenstein in his later writings, which are written in a sort of a poetic, hard-to-understand language, but he's trying to get at the idea that you might not want to adopt this view when he writes, "You say the point isn't the word, but its meaning, and you think of the meaning as a thing of the same kind as the word, though also different from the word. Here the word, there the meaning, the money and the cow that you can buy with it. But contrast money in its use." Right, so before getting back to that, a variant of that position that Bender and Kohler present, and another very common view, is sort of the classic referentialist position, which sees meaning as a relation between a word and its grounding in the real world or model of the world, so that the meaning of chair is there's these things, it's this big set of chairs, that's the meaning of chair. If you sort of think about that one, you might think, well, a pure large language model then doesn't have any notion of meaning. But if you build a visual language model, well then, because it does connect between words and pictures of things, then a visual language model does have a model of meaning. So visual language models understand, but large language models don't. That seems kind of paradoxical to me, not least because in practice, the vision part of visual language models to this day is pretty bad, and nearly all the intelligence seems to reside in the language part of it. So the alternative, which is essentially what Wittgenstein develops, is he argues that for a large class of cases, though not for all, in which we employ the word meaning, it can be defined thus: the meaning of a word is its use in the language. And so this gives us the inferentialist position, or the use theory of meaning, that we think of meaning as understanding appropriate context in which something can be used, where that context could be a purely textual context, or it can be the real world, a sociological context, all aspects of context. And you might think in some sense the real world is privileged, but it's not the only way that we can ground meaning, right? All the time people generate science fiction worlds, and we can understand what might be appropriate or not appropriate to say in a science fiction world, even though it has no physical real world grounding. This kind of inferentialist position is also the position Turing took in his 1950s version of what is artificial intelligence. And I think an interesting feature of this definition is, if you're thinking about understanding context for use as your definition of meaning, then it makes sense that you have a gradient sense of meaning, that you can partially understand the right context for use, or you can understand them rather better. And I think that's true for most human language use. And so an example I used a couple of years ago on a brief paper I wrote on human language understanding, is I used this example of what is the meaning of Shania. And well, one possibility is that you've seen and held one, and you know everything about it, and you have a classic grounded meaning. But if that's not the case, well, I can put up a photo of one, and then you've got some idea of what one is. But if I don't show you a photo of it, I can... Oh, sorry, I left out a bullet point. Even showing a photo of it doesn't tell you everything about it, because you'd know more about a Shania if you'd heard one being played. You know what kind of sound it makes, right? So if you've only seen a photo, you've got a sort of a partial meaning, perhaps. And if that hasn't happened, if I tell you about it, if I say it's a traditional Indian instrument, a bit like an oboe, well, surely you know something about the meaning of the word there, though perhaps a little less than if you'd seen it and heard it. But I could give you more information through language. If we move to the language model case, you don't get a definition like that, but you're going to get a piece of text or pieces of text. And so, for example, you might have seen this piece of text from the novel An Atlas of Impossible Longing. From a week before, Shania players sat in bamboo machans at the entrance to the house, playing their pipes. Bikash Babu disliked the Shania's wail, but was determined to fulfill every conventional expectation the groom's family might have. And so there's something interesting there, right? That if that's the information you've seen, you know something about it as being a musical instrument. You don't know as much about what one looks like as if you'd seen the picture. But on the other hand, in some ways you know more about a Shehnai, that you know cultural connections, that it's associated with weddings. You know something about the sound of it sounding like a whale that you wouldn't have from having seen a classic grounded meaning of just having held the instrument or looking at a picture of it. And I think that's actually the kind of meaning that we really have for language a lot of the time. All kinds of the words of language, we sort of 2/3 understand their meaning, but there's lots of subtleties that we're missing out on. Okay, so that's meaning. I sort of wanted to say then a little bit about intelligence. Since ChatGPT, when people appear on television talking about artificial intelligence, it turns out that usually they're talking about large language models. So are large language models artificial intelligence? And so what is artificial intelligence? Well, I take the artificial part as fairly straightforward. And so the difficult part is, what is intelligence? And we might wonder as to sort of the relationship between language understanding and generation compared to general intelligence. I mean, I think of the two of them as extremely associated. So there's been some recent neurolinguistic work from Ev Fedorenko's lab when they try and look at separate out the language parts of the brain versus the thinking and reasoning parts of the brain. But I think that ends up a little bit reductive, because what they sort of end up saying is the language part of the brains are only the parts that are doing low-level phonetic processing, because the reality is all of the higher level language understanding and generation is happening in parts of the brain that are used for all kinds of thinking and reasoning purposes and not being used exclusively for language. So what then do we say about this intelligence? So last year, California started passing various pieces of legislation and failing to pass various pieces of legislation about AI. You might have heard of some of them. One of them that you probably haven't heard of, that was kind of much more obscure, was in section 11,546.455. I guess there's a lot of California legislation. California wrote into its legislation a definition of artificial intelligence. So for the state of California, artificial intelligence means an engineered or machine-based system that varies in its level of autonomy and that can, for explicit or implicit objectives, infer from the input it receives how to generate outputs that can influence physical or virtual environments. So I think this is a terrible definition of artificial intelligence. In particular, it fails the landmine test. Now, I'm not wanting to advocate for landmines, but I think you have to note that a landmine satisfies their definition excellently, right? It's an engineered system that has a level of autonomy, yeah. It has a very explicit objective of maiming and killing people. It receives some input, someone steps on it, and it definitely generates an output when that happens, which has a big influence on the physical environment. But I think we don't want to say that landmines are intelligent, so there must be more subtlety to it than that. So, where else can you go for definitions of intelligence? I think a lot of times humans, even when talking about other humans, confuse knowledge and intelligence, right? We go around and say things like, oh, my tax guy's really smart. He knows the tax code backwards, where that's really, that person has a lot of knowledge. And so that's not a very good definition, I think. And then you see definitions of artificial general intelligence like ability to perform most economically valuable tasks at or above the level of the average person. Now, if you're an economist wanting to look at how the world of work is going to change with the deployment of artificial intelligence, this is probably a fairly relevant definition, but I don't actually think it's good as a definition of intelligence, because the reality is a huge amount of what most employees do in jobs is actually very routine, and very routine things are easily automatable, but they're not really intelligence. When the Stanford Human-Centered Artificial Intelligence Institute came out a few years ago, a little job I got tasked with was writing some definitions. And so I wrote this definition of intelligence: the ability to learn and perform a wide range of techniques to solve problems and achieve goals appropriate to the context in an uncertain, ever-varying world. I think this definition has some good attributes. And that's because it sort of focuses on the fact that the world keeps changing, and so we have to be able to adapt to it, and the central tool for that is learning. That I think when we sort of get down to it, that really the central thing that intelligence involves is working out how to behave in a near optimal way in changed circumstances. And I'd argue that that's actually not something that large language models can do at all, right? Large language models have been highly successful because they've essentially been able to suck up, by reading the internet, all of the hard-won human knowledge of the past centuries and can reproduce it and do things that look sort of like reasoning over bits of it. But it's not really like they're adapting to anything that's changing in the world. They're backward-looking sources of knowledge. Okay. And so that although in some sense we can see reasoning, we don't necessarily seem to have all forms of intelligence. You know, so the latest buzz is now that we have test time scaling, or thinking and reasoning happening with models. And so on the one hand, these models can do quite incredible things. So this is DeepSeek doing fine 2 3-digit palindromic numbers that sum to a 4-digit palindromic number. And it goes into thinking mode, and it says, you know, okay, I need to find 2 3-digit palindromic numbers, ... First, what is a palindromic number? It's a number that reads the same forwards and backwards. So I need 2 3-digit numbers, both palindromes, that add up to a 4-digit palindrome, blah, 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 blah. And it, there's been this wonderful, again, unexpected development by getting language models to sort of just banter on like this for a long time. They can think their way through problems and produce amazing results. So after producing thousands of more lines of text, it can start to have figured out of, okay, well, what I need, this is getting a bit small for me to read, I'm afraid, is I need 3-digit numbers where the first and the third digits add up to 11, and then constraints on the middle digit, and it finds solutions like 202 plus 909 equals 1111, or 212 plus 989 equals 1221, and it can solve it. I mean, it's just amazing the way you can get these large language models to now solve quite different, difficult math problems. Amazing, amazing. But you know, a lot of this is still kind of a glass half full. You know, on the one hand, you can see sort of amazing abilities. So here's a little kind of reasoning problem. If the town is Twee is 12 kilometers from the town of Wallop, and the town of Golis is 18 kilometers from the town of Twee, what is the maximum minimum possible distance of the town of Wallop is from Golis? And it can reason through this and give exactly the right answers and lay it out in beautiful markdown. And it looks like, oh, this language model understands the world and how to do these problems. But it turns out then you can do something just to push a little harder. So I push a little harder and add one more town, the town of Ansell, that's 5 kilometers from the town of Golis. And this isn't a much harder problem. I kind of think, you know, probably if you give this to a 9th grader or somewhere around then and say, can you figure this out? They'd be able to figure it out, as I've shown, and come to the conclusion that, well, the town of Ansell can be a minimum of only 1 kilometer away from the town of Wallop. But, you know, somehow then the large language model gets confused it finds the maximum distance correctly, but then for this minimum distance, it lays something out which makes no sense at all, and it decides that the minimum distance is 25 kilometers. And at that point, you're sort of left wondering, is this thing really thinking and reasoning as a human being does? And, it's kind of complex. On the one hand, these models seem to be making progress, and they seem to be able to start to do more stuff than many people thought was possible. Let's see if my little video will play. One of the people who's always been very down on large language models is my good friend Jan LeCun. As a vision person, somehow he thinks that the 3D spatial world and reasoning in it is really what intelligence is about, and language use is some marginal communication mechanism that isn't very much connected with intelligence. But he's sort of been repeatedly proven wrong as to how much you can get out of language, as in this clip.
I don't think we can train a machine to be intelligent purely from text. So for example, I take an object, I put it on the table, and I push the table. It's completely obvious to you that the object will be pushed with the table. There is no text in the world, I believe, that explains this. And so if you train a machine as powerful as it could be, your GPT 5000 or whatever it is, it's never going to learn about this. That information is just not present in any text.
Okay, but the reality is you didn't even need to get to GPT-4. In the ChatGPT days of GPT 3.5, it could do exactly that reasoning. So, that raises the question of, what is the limits of large language models? Despite the funny clip, I think I actually am tempted to agree with Jan LeCun. I just sort of don't believe that making these autoregressive text prediction machines larger and larger is really going to get us all the way to having artificial intelligence. And I think perhaps one of the gaps is that if you look at the analogies with human learning, what has been found is that for human learning, it's all important to have interaction, that you just don't get human learning from a little human looking at stuff in the same way that a large language model just looks at stuff that other people have produced, that you really need to get the kind of causal input that comes from doing experiments. So this is the position that Alison Gopnik has advanced in her work on The Scientist in the Crib, that to argue that when your darling child is knocking everything over in the household and causing you work, that actually they're doing important experiments, and that is the way that they come out to be intelligent, knowledgeable human beings. Gosh, I've talked a bit too slowly on that part, so I'm a little bit behind, I'm sorry. But I should now skip ahead to tell you about the more technical part and say something about our work on direct preference optimization for steering large language models, which I did in collaboration with a bunch of people shown here. So when we have these large language models, what kind of things do we want to be able to do with them? We'd like to be able to get them to, do things like write performance reviews for us that we don't want to write ourselves, or we'd like them to read long novels and tell us what the plot was, or we'd like to sort of chat with various kinds of bots. And, for the story I told before about the development of large language models, I sort of left out the piece that really made this all possible, and that was you don't get this simply from training a huge large language model, because if you sort of train a huge large language model, it's very good at predicting, text that could follow after that piece of text. But if you ask it something like, explain the moon landing to a 6-year-old in a few sentences, as likely as not, the text it's going to produce next is text like, explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old. It'll produce some kind of text that's related to the text you gave it, but it won't typically answer your question or follow your commands. And so to achieve the ChatGPT moment, what OpenAI did was then to do a further process of training, RLHF, reinforcement learning from human feedback, where you were post-training the large language model with pairs of responses to questions and commands, and telling it you should give A and not B, and that was the way to get models that responded like a person would. And even though earlier large language models, it seemed exciting to NLP people, it was only when this was done that the models became exciting to the whole world, because they made them responsive like human beings were. And so the steps to build a large language model sort of became like this. So first of all, you built on tons of data in this unsupervised pre-training way an enormous large language model. Then what you did was you found some data that's like the data that you really want the language that you really want the model to produce, maybe dialogue data or something like that, and you do further training of the same sort but on a sort of a specialized subset of data. Then you generate from that model pairs of responses to a prompt, and then you train a reward model as to which of those, how much reward, how good are those two responses. And so for the reward model, you're taking for a prompt what are two possible responses, and then you're wanting to fit reward scores to those two responses, and that's being done with the Bradley-Terry model, which is a very traditional stats model that goes back to the 50s, where you're assuming that the probability of choosing the winning response over the less preferred response is equal to the logistic of the difference in the reward, where each reward is a numeric score. If you play something like chess or Go, you're familiar with this kind of model being used for ELO scores, where the player gets a numeric rating and you get a probability out of it. Okay, so then once we've got that model of the probability of winning, we can then get data about what thing was said in response, and then we can sort of work to minimize the negative log likelihood by then altering how much reward you give to different sentences, and then you've trained a reward model. And so then what you did in the RLHF model is, once you've got the reward model, it's then your job to build a policy that tries to produce sentences that optimizes the reward. That's what the general sort of RL playbook is all about. And the way that was proposed to do that was by an algorithm called PPO, Proximal Policy Optimization, which is an actor-critic reinforcement learning model. And so at the end of the day with this, sort of doing this PPO optimization ended up with this sort of very complex algorithm. This diagram comes from a recent paper that was hoping to explain to you how PPO works so that you would understand it. But I count this as a negative training example, because this diagram is so complex. I stare at it and it gives me no idea as to how the PPO algorithm works. And in honesty, the PPO algorithm is kind of a complex, cantankerous beast. I mean, it's not only that there's a fair bit to understand, it's actually very difficult to get right, that it's, actually sort of very unstable and cantankerous and difficult to have it perform well. In fact, that was sufficiently the case that basically the situation until 2024 was that the people at Anthropic, OpenAI, and Google use PPO to do this kind of steering of large language models, and everybody else thought it was too difficult to try, and no one else was involved in the game of steering large language models. But so what we were thinking about is, well, looking at this picture, it sort of seemed like surely this doesn't have to be this difficult. I mean, firstly, there was a lot of RL talk here, but if you just sort of look at it as a dumb NLP person, it seems like there's a lot of talk about different things, but really, you know, everything's a large language model. You start with a large language model, the reward is being measured by a large language model, and the policy, well, what's a policy in this context? It's something that generates next words, and that's a large language model. You know, this is sort of turtles all the way down. Everything's a large language model. Why do you need so many things and all of this RL stuff? I mean, in particular, it feels like this isn't really kind of real RL, because what we're doing is offline RL, where we've just got a prompt and two responses, a good one and a bad one. Why can't we just do sort of regular machine learning on that? And so that's what we worked on with the direct preference optimization algorithm. And so the idea of this algorithm is that if we come up with a clever way to parameterize our reward model, then what we'll find is that we can actually just read out the optimal policy for that learned reward model in closed form without doing any further iterative fitting of a policy very cheaply. And so this is the idea of how you do that. So we start with exactly the same RLHF objective, where what we want to do is maximize the likelihood of the things observed being expressed in terms of the reward, plus an extra term that I haven't mentioned. We're also constraining our optimized model to stay close to our beginning model. So the idea here is that these large language models have been trained on a fantastic amount of text in the first stage, whereas we're using a fairly small amount of preference steering data, and so there's probably lots of stuff that never appears in that. So we want to be careful to say we don't destroy all the rest of the behavior of the large language model. Okay, so if we take that RLHF objective, it had already been proved by Peter Abeel and colleagues earlier that RLHF objective has a closed form optimal policy associated with it, which is shown in this second line here. That's easy enough to write, but the problem with that is that you've got this 1 on Z normalization term. And whenever you see these Z normalization terms, you know that they're kind of bad news. But this one is especially bad news, because if you're just seeing one in something like a next word prediction model, you're normalizing over the entire vocabulary of tokens, which might be large, but is in practice doable. But here, you're normalizing out of every possible completion of the document. So you've got this sort of huge exponential space that you couldn't possibly normalize over. But, well, it turns out you can make some progress. So with some fairly simple math that's simple enough that even I can do it, if we just rearrange that expression, we can write an expression for the reward. And that sort of doesn't look like you're making progress, because we've still got the Z there. It's just been rearranged where it appears. But actually, this is sort of thinking about it that way as all you need to make progress, because if we remember back to the Bradley-Terry expression, the Bradley-Terry formula was calculated in the difference between the rewards of the two items. And so then, lo and behold, if we're going to take the difference of two rewards for the Bradley-Terry form, then that means when we're going to be cancelling out those two Z terms because they're the same on both sides, and we're only left with the rest of the expression, our induced reward for the winning and the losing cases. And so now we've got something that we can successfully deal with. And so that's what we do in the DPO algorithm. We've got this sort of simple loss over pairs, which will be able to optimize the original RLHF objective, but in a straightforward way. And so that means that compared to the original picture, we can now simplify it by getting rid of the iterative learning of a policy and just say, well, we can fit the reward model, and then that just tells us in a simple trivial transform what our policy is. I mean, to say one more remark about that, I mean, you know, really when you're doing this offline, so-called offline RL to RL people, when you have these kind of pairs, I kind of think of it, you're not really doing RL at all, right? Really what you're doing is what's been explored in other places as contrastive learning. And there are lots of places where lots of neural net people, including me, have used contrastive learning for sort of a decade. And so really, this is just like other contrastive learning, apart from its contrastive learning fitted into the Bradley-Terry objective. And so we started doing that. And so here's an early experiment that we did where the idea was that we're going to steer a language model to produce either very positive or very negative reviews of movies. And so we explored doing that with different algorithms. So down the bottom in the sort of bright green, we have where you get to if you just do fine-tuning to the preferred output. And you know, that gets you somewhere. You get a reward of about 0.6, but it illustrates that, you know, simply using further supervised fine-tuning doesn't work very well to optimize the reward. I should actually mention what the axes of this graph are. The x-axis is how far you're wandering away from your starting large language model, because we wanted to constrain how far you wandered. And then the y-axis is how much average reward you're getting for your generations on a scale of 0 to 1. So you can do better than with that with RLHF algorithms. So we started with Hugging Face's TRL RL library, and that's shown in the purple. And the purple does exceed the bright green, but it doesn't actually work great. It seems like you're getting a maximum reward of 0.8. And, you know, I take this as further proof of how it's actually really difficult to get PPO to work well. So we thought, oh, surely PPO can't be that bad, and maybe we'd better start seeing if we can debug and fix up the Hugging Face PPO implementation to get it to work somewhat better. And indeed, we were able to. So in the orange version is our further work on the PPO algorithm. And look, we got the PPO algorithm to perform rather better, and you know, up to a certain point it's starting to get up to about 0.9 reward, but somehow our implementation goes a bit unstable, and if you wander further away from the base language model, as you can see, then there are a couple of orange dots over there where it's gone back down to around 0.8. Subtle stuff, these reinforcement learning algorithms. Whereas the DPO in yellow, isn't that beautiful? Like, just very quickly it zooms up there and gets a reward of 1. Okay, so that was great, and you know, at that point we thought, oh, will anyone believe this? We really probably need to show that we can steer a large language model, and would they believe us if we did it with a 7 billion parameter model, or do we have to find enough GPUs we could do it with a 13 billion parameter model or something like that? But, you know, we stuck up our paper on archive with the results we had at that point. And, you know, then a miracle happened, because I guess these results seemed interesting enough that other people started using it on models for us. So the people who are actually our good friends at Hugging Face, they started exploring what you could do with the DPO algorithm, and they trained a 7 billion parameter Zephyr model with DPO, and that worked great. And so then other people took up this idea and started producing better steered language models on other models. And, you know, precisely what was great here was that DPO was so easy to run that you didn't have to be sitting at OpenAI. You know, it was literally the case that if you were, had a good gaming box with a couple of 4090 GPUs in it, right, you could be running DPO on a 7 billion parameter language model, and so lots of people were, and then there was sort of this sort of competitive how you could improve your preference tuning data sets to get better and better results. And then soon people started using them for bigger ones, so the people at AI2 scaled this up to 70 billion parameter language models, and now things have made it everywhere for vision, for image generation models, but also the biggest one is that Meta has now been using DPO as part of their optimization of their llama models. I did have one more bit, but should I maybe stop and take questions at this point, since that's the main story?
How much more do you have? Because we have another 30 minutes. And then
I mean, not much. I guess there's about 5 minutes left. Okay. Do you want me to do it?
Yes.
Okay. Yeah. So, I mean, this is just the coda to the story. Yeah. So, I think, DPO is a nice, simple algorithm. I commend it to you. But, I think in retrospect, what's really interesting is that the things went like this, right? So Peter Abele had this clever student, John Schulman, and Peter Abele's a reinforcement learning person, and, John Schulman learnt reinforcement learning. He did robotic motion planning with Peter, and developed some of these algorithms. He then went to OpenAI, and starting off with, this was sort of before OpenAI got jazzed with language models, and they used to do things like playing Dota 5 and other kind of video games using reinforcement learning. And it was in that context that he initially developed and applied PPO, and then later on he was told, John, we're not interested in playing games anymore, we want you to apply RL to large language models. And so PPO came to large language models, and essentially by this point, since John Schulman was the god of RL and they'd done this wonderful work with ChatGPT, everybody assumed that the only good way to produce steered large language models was to run the PPO algorithm. So you either ran PPO or you thought this was impossible for you to do. And the sort of really interesting thing was, after we published DPO, that kind of just caused a brain reset in the community, and everyone thought, there are other ways you might be able to do this. Maybe this DPO algorithm isn't that special after all. There are all kinds of ways we could start thinking about doing preference learning to steer large language models. And so, and so then very quickly a whole bunch of different algorithms started coming out. There was CPL and IPO and KTO and SymPO. And, I don't honestly want to claim in any way that, DPO is better than any of these other algorithms. At least a couple of them have distinctive advantages, right? That really, I think the long-term impact of DPO will more be, proving that you could do this in other ways, which has then led to this very active new field of research. I will skip that one and go to this one. So my final admonition or encouragement for the students is, I think there's been a bit of a malaise among students in this current era of AI, of thinking, the people at OpenAI and Anthropic, they have tens of thousands of GPUs and they've got all these people and blah, 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 blah. What can I possibly do as a student? And I think that that's just absolutely wrong. That the reality is that these companies are so fixated on producing, humongous so-called frontier models that the end result is that they're doing this very heavy, large-scale engineering infrastructure. And if you're doing very heavy, large-scale engineering, you end up incredibly conservative. You're in this world of, this run's going to cost us $20 million. We don't want anything to break. This way of doing it works. Just keep with it, boys, and it'll be okay. And so, just a lot of things aren't explored in these companies. And, it doesn't matter what level you're working on. It's whether you're thinking about the steering of models or more effective systems level work, or you're thinking about how different data mixes are important, or different model architectures. There's just very little exploration happening at the large language model providers. And so I think the right way to think about the world at the moment is that, although certainly the NLP research world has changed in the era of large language models, it's been reinvented in such a way that everywhere you look, there are new problems that have barely been explored and considered. And for the vast majority of those problems, you can start working on them in the small and tinker with other ways you can do things. And, at least if you're lucky, if you can come up with some ideas for different ways to do things and show that they're useful in the small, well, actually, other people will run them in the large for you. And, I think that's actually even, the right way to think about university research, right? If you're an aeronautical engineer at a university, you're not trying to build a better airplane than Airbus, right? That's just not a conceivable thing, but you're wanting to do some kind of exploration of airfoil shapes to show that there's a better way to design a wing or something like that, and hoping to do a prototype that other people will pick up in the larger. And I think that that's the same for the world that we're now in with modern AI models. Okay, thank you.
Brilliant way to end, right? Be small and be clever. You don't need money, you don't need size. Please, if you have questions, we have about 10 minutes for questions at most. Please line up at the microphone. First come, first served. And then, Chris, you'll just stop when you get hungry. There's tea and snacks and all that out there. And that's waiting.
A brave first person. Okay.
Very first person. Hi, Chris. Thank you so much for this talk. It was really fantastic. My name is Nina. I have a background in aerospace and actually did my master's degree.
I don't.
Did my master's degree at Stanford with Michael Kokendorfer, who I know is in HAI with you. And I'm here in my capacity as part of the investment team with Tin Alley Ventures, and we invest in University of Melbourne research. But on nights and weekends, I have been exploring the idea of more active agents and building context windows with multiple layers of abstraction that go in and kind of track in and out the intent of the agent and how she's steering the conversation in a more macro sense. And the behavior has become quite impressive to me. Even though I've built it, sometimes I'm shocked that it can do things that are so great, and sometimes it really falters. And so I've been thinking that this steering at the decision level, like, is this the appropriate time to change the node? She's keeping that in mind about her intent for the conversation while also outputting responses to the user as one instance. How to integrate this to make it more consistently making the right conversational steering decisions at the linguistic level, where 80% of the time it's good, 20% of the time it's not. And I'm wondering if you've seen anything like that. I'm starting to get across the literature, but I'm not super current in LLMs. So any kind of approaches where they are stacking abstractions within a single context window, agnostic of the LLM, and then approaches to like fine tuning to get those results better.
Yeah. I'm not sure I've fully seen things like that, but I mean, one thing I will remark is that, you're talking about kind of multi-turn interactions as to putting together dialogues. And I mean, something I probably should have said was, I'm really not wanting to say, oh, don't do RL. What the message really was that in terms of the sort of when you just have single turn preference data, then RL really isn't necessary. But I think what we're increasingly moving into is a world in which you want to do information seeking dialogues and be considering 5 turns and where is the conversation going. And once you're in that kind of space, then I think you actually really do need to do RL, and that will, so I think real RL will increasingly become important. And actually some work I've been doing recently with a student has been looking at sort of long horizon searching tasks, right? So that's sort of when people are sort of trying to get information in a browser, that they're often sort of doing a whole bunch of searches with a long-term objective. And there, by doing RL, you're getting better results because that you're doing this sort of multi-turn optimization where you're succeeding there. And I think that's probably the case in your kind of context as well.
Yeah, one of the concrete examples. Oh, sorry, move on. Sorry.
Thank you for the wonderful talk. I have a question about the hallucination most large language model has. I'm sure most of us has experienced once we ask hard questions, especially ask hard science questions to those large language models, they usually give us semantically wonderful answers that look like grammatically coherent, but most of the time have scientific effect errors in it. In contrast, for human experts, many times we experience whose first language is not English, they give answers, talks in language we say broken English, have grammar errors here and there, but the facts usually are very accurate. There's huge contrast between that. I have a feeling that has to do with, as human, the needs we have to figure out what is right and what's wrong is built in ourselves. But the large language models usually have the needs that are imposed by us. Right? We as human, as designers, got to decide what the reward is, how much reward it is. Do you have?
Yeah, I mean,
what do you think about that?
I think it might even be simpler than that. I mean, this is, again, connected to sort of, what do we have in the form of large language models, and are they, really the ultimate path to, reasoning and intelligence? I mean, I actually think that ultimately it'll be proven that our current LLM model is just wrong for the purpose of reasoning and intelligence, because the whole model that they're built around is, here is some context, predict a likely continuation, and which is done probabilistically. Now, if it's about some well-known real facts in the world, normally it gives the truthful answer because that's the highest probability, but to the extent it doesn't know the truth or heads off in some direction, or just tell a story, right? And I mean, on the one hand, that was part of the early successes of large language models. You started asking them to tell a story about unicorns in the Andes, and it writes a nice little story. But, on the other hand, there's sort of nothing else there apart from write plausible text after this continuation, whereas I think most human beings, there are few exceptions like the current US president, but most human beings have a sort of an idea of what things are true in the world, and even though they might be able to tell a good yarn when they're down the pub, that they can differentiate between things that are facts versus things that they're telling a good yarn. Whereas, really there's no sense of that distinction in our large language models. So, I mean, I think ultimately we might need quite different models that really have much more in the way of an episodic memory, where they actually know about the facts that have happened in the past and work from there. And, although there are lots of practical steps you can make to, reduce the amount of hallucinations, and that's good for a lot of practical applications, I think the whole architecture is sort of wrong for really getting rid of them.
So I have a question about one of the goes crazy and doesn't know what to do. So there's been like a research direction that tries to combine symbolic methods with the LLM, which is called neurosymbolic reasoning. And yeah, I just wanted to ask, do you think that in the future, for more robust reasoning, that is the direction? Because in the research I've been exploring, we see that for counterfactual variations like that, there is a more like equivalent performance even for counterfactual differences and the normal problem description. So I just wanted to ask whether you think that's a future research direction that can emerge, that neurosymbolic methods are more stable in
Yeah.
reasoning.
I mean, if I'm honest, I'm a little bit skeptical on neurosymbolic methods. I mean, there has been some neat results in various areas, but I think it's just also ends up extremely problematic trying to explore neurosymbolic methods. And the problem is that the symbolic and the neuro just don't work very well together, right? That the whole power of neural methods is you're making this continuous relaxation, and then once you've got a continuous relaxation that you can, straightforwardly with your automated calculus propagate gradients through many layers and learn these amazing complex systems that let everything unbelievably marvelous like math problem solving that large language models can often do just emerges from this gradient-based learning. And the problem is, as soon as you try and mix in some symbolic stuff, it then breaks all of those gradients. And so I'm sort of skeptical that that's actually ends up the right path forward. But, it's obviously good for different people to be different, exploring different things, and we'll see where things get to.
Thank you.
Hi, sorry. So I'm a data scientist in bioinformatics. So I'm trying to tell that the ARC AGI2, which is the data set which is created by sorry,
Francois Chollet.
Yeah, Chollet. And he argued about the reasoning of in symbolic interpretation, compositional reasoning, and contextualized rule application. So I want to ask you if it's on the Kaggle dataset, there is a competition going right now. So I just want to hear your thought about this. Thank you.
Okay, yeah, so Francois Chollet was the person who sort of pioneered the Keras deep learning framework that some have used, but he's also has actually, I think, a lot of thoughtful things to say about artificial intelligence. So he developed this ARC challenge, and then once systems started to get good at that, then came up with this second version of the ARC challenge. I mean, and seeing this as maybe this is a better instantiation of are these machines intelligent than some of the more linguistic tests. I mean, so I think it's absolutely interesting and good to have people exploring in different directions. And so, it's a great data set to look at and think about different problems. I mean, I think in some sense it's in good directions of looking to see whether models can work compositionally and see various reasoning patterns. I mean, I think, though, he thinks it's a bit more special than it is, right? Because, I mean, it's sort of inspired by a style of problem that is often used in human IQ tests where you're showing people visual patterns and getting people to interpret that. And, that's a skill. It's a skill that at least early on was very difficult for foundation models, because most of them, their visual reasoning was very underdeveloped. And so at the time he first started down this path, the models didn't work at all on this. So some of the more recent models, like the recent Gemini models, are quite good at the original art challenge now. You know, so it's another angle to explore. I don't think it's quite as much the other angle that you should be exploring as he seems to think it is.
Thank you very much. Really grateful for your talk. I invite you now to enjoy some snacks and tea and coffee. Chris is around for a little bit longer, and then he has further meetings to go to. Our next talk is next month, so please look out for the announcements.
The only thing you have to do is people like
If you want, I'll tell the team.